What's up, physics? It's snow day, and so the only way you're going to learn is if you're going to watch TV. So we're going to bring physics to TV. Just when you thought it couldn't get bad enough, turns out batteries have resistance too. Let me prove it to you. That's right, batteries have resistance. But I thought batteries had voltage. They do, but now we have to learn how they have both. So you can see that I've got our voltmeter hooked up to the positive and negative terminals of the battery, and we've got 5.4 volts. But if I connect the light bulb into the circuit, we see that this voltage drops down to about 4.9. And then you unhook the light bulb and it comes right back up to about 5.4 again. And so you're wondering, what could be going on inside this battery that makes the voltage drop? Well, remember, the only thing that makes voltage drop is resistance. And so when current is flowing, there is a voltage drop. When current isn't flowing, there isn't a voltage drop. Let me show you what's going on. If we make a circuit diagram, what we can see is that inside the battery we've got something labeled E, which we'll call electromotive force. Electromotive force, also known as EMF, represented with squiggly E, is any potential difference that can cause charge to flow. That's what an EMF is. So sometimes EMF, voltage, potential difference, they all actually same sides of the same coin, different sides of the same coin. So as we look at our little circuit here, inside the blue box is what the battery is. And you see the battery has a little internal resistance, little r. And as current flows through the circuit, current has to flow through that little r as goes through the battery. Now, everything's kind of just all, there's no little itty-bitty resistor embedded within here. It's just a fundamental part of the chemicals and the construction of the battery that there's still some resistance to the flow of charge, even though there's a chemical reaction giving electrons a push. You're not dismissed. So, inside the circuit we've got I times R, which is the voltage drop of the light bulb, and then we've got I times little r, which is the voltage drop across the internal resistance of the battery. But then we've got the EMF of the battery that makes the current flow. If we put this into Kirchhoff's loop law, remember the loop law says that all your voltage gains have to equal your voltage drops. So our voltage gains would be the EMF of the battery, and then our voltage drops would be the two resistors. That's how the math comes up. When you want to find the internal resistance of the battery, you kind of need to know what's going on in your circuit, and you can measure that with an ammeter and using a resistor of a known resistance. And with whatever you're given, that's how you can then usually solve for the resistance of the battery, internal resistance of the battery. There's also something known as the terminal voltage, and that's what I'm measuring right here, the voltage at the terminals. And so the terminal voltage is whatever the EMF of the battery is minus I times R, minus the drop across that internal resistance. That's how you can calculate terminal voltage. So between these two equations, you can get anything you need to get when a question asks you about internal resistances, but that's how it works.